So in last week's session, we looked at two example problems. One of them was this deterministic HJV problem. So we have our control or our cost here. There was a component of the cost that was dependent on our control, so quadratic in the strength of our control, and another component that was on the terminal state, and it was quadratic in the value of the terminal state. So penalizing terminal states that stray away from zero. And then our stochastic problem was exactly the same, except we wrote it with in terms of expectation, because we had a stochastic process rather than a deterministic process determining the transition of our state. And so in that case, in order to have a deterministic control cost, we express it in terms of expectation. So hopefully this looks familiar, but just to recap what we found a HJV equation. Welcome. We found an HJV equation for the deterministic case. I'm just recapping what we derived last week. We're going to build off of it today. And then we found, we found a HJV equation as well for the stochastic case, with the main difference being the inclusion of this second derivative term, which was a result of the infinitesimal generator that we derived. So we get this diffusion term because of the Brownian motion that is generating the stochastic process. We have the same terminal conditions in each case, and what we found is that in both cases, we found the minimizing u by finding the vertex of a parabola, because both these expressions here are quadratic. I'm just recapping things from last week. So both these expressions here are quadratic, and so we found that this u star minimized our the argument of our HJV equation. We were then able to make this substitution into our original PDEs and find a solution given our terminal conditions in either case. So what we found is we found this for the deterministic case, and in the stochastic case, we had to append this temporal function, add it to our the cost to go. That's what we call this v, is we call it cost to go. We added this temporal function to our cost to go in order to get rid of this second derivative in our stochastic case. And what we found is, because we had only added this temporal function, in either case we had the exact same control, because our control just depended on the spatial derivative of v, our cost to go, and because we were just adding a temporal function, it didn't change our spatial derivative. So we found we had the same feedback controller in either case. And remember, a feedback controller is one that depends explicitly on the state. And then we were able to also derive a feed-forward controller in the deterministic case, and we found that had the form of a linear function, or an affine function rather. So the optimal trajectories in the deterministic cases are just these straight lines that don't quite go down to zero, but rather strike this balance between the terminal cost and the control cost. In offline, I also derived this expression here, which is the variance of our stochastic process. And we see this thing is going to be less than or equal to sigma squared t, which is what we would have in the case that we weren't implementing a control. So this is an uncontrolled Brownian motion. You would have this amount of variance. But this is the variance that we have for our control process. And then if you're interested in seeing the covariance, it looks like this, I believe. So those are our results from last week. And also, I didn't mention, but this is our explicit form for our so this is actually our feed forward control, and then this is our trajectory resulting from that feed-forward control or the feedback control. They're the same equivalent in the deterministic case. So that's the recap from last week.
I have a quick question.
Yeah.
So how does feedback control versus feed forward control different?
So in the deterministic case, they're exactly the same. I just we solved for x of t by using this ODE, plugging in our expression for u, solving for x and plugging it back into u. But in reality, there's always some level of noise in the real world. In the real world, there's always some level of noise that corrupts our dynamics. So the real world almost always looks like the stochastic case, unless you're in a very highly controlled environment or maybe doing a computer simulation or something like that. But there's always some level of noise, and the issue with using a feed-forward control is you're not making use of information about your current state. So if you deviate from what you expected the state to be, then that you could have that error that you've introduced gets magnified, and you deviate exponentially from the path.
I see. So yeah, I guess I don't know what it means to be like feed forward versus feedback control, but so would that you start XTB feed forward?
In this case, we would call it feedback. It'd be a feedback
Right.
control. So the control
It depends on X, that's why.
Yeah, it just depends on X. So in in a real control problem, not only are you gonna have some noise in the dynamics, but oftentimes you only have observations that correlate with the full state and aren't the full state themselves. So in this case, we're making the assumption that we have a perfect measurement of the actual state. So in any real scenario, we're gonna have something like a measurement y that is equal to some usually use h plus some noise term eta.
Yeah.
That's the real scenario, but in these optimal control problems, we're often making just the assumption that we have access to the actual state.
Yeah.
But in reality, you're gonna have some partial observation of the real state.
Got it.
Good question. Okay.
And what is the meaning of T and S, covariance?
Oh, they're just they're different time steps.
No, the symbol, the conjunction of T and S, use of.
Oh, sorry, yeah. This is a propolis that use of the wedge product. It just means minimum in this case. Yeah. Yeah, good catch. Okay, so today we'd like to move on to this drunken spider problem. And the way this differs from the previous problem is we're going to be adding a state and time dependent cost variable, cost function, to our overall cost. So previously we had an expression for our cost like this. We're gonna remain in the stochastic setting, so we're still considering expectation. And now we're gonna have something that looks like this. So take the expectation, we're still gonna have that control cost. So 0 over to our over to t, the end of our period. CU, again, we're looking at a quadratic case, CU squared. Maybe I can make the dependence on t explicit. And now we're also going to consider a phi dependence on xt and t. So this is our new state dependent cost. And I'll illustrate that in a second, but I also want to include our terminal state cost that we had as well. So this is our new optimization problem. We have to, say what our dynamics are, and later on, we're gonna look at, we're gonna stay in the kind of steered Brownian motion paradigm that we were looking at last week. So we're gonna have dynamics of the form dxt is equal to u dt plus sigma dvt. So it's the same sort of diffusion process that we had last week. So this is the new term that we have here. And the reason why we want to include this is we want to look at a problem like this drum and spider problem, where if we enter this body of water, we're going to suffer some extremely high, potentially infinite costs. So we can capture this sort of arrangement and more general arrangements by including this fee term here. So to illustrate that, maybe we have that, maybe drawing some ISO curves for fees and level sets. We might have some fee that looks like this, and maybe it's 1 in here, 2 in here. Or we also want to look at the case where we have potentially infinite cost, and then maybe it's 0 everywhere else. So these are different illustrations of what our fee might look like. And then again, this is the sort of spatial temporal domain that I was using last week, where we have x and t. Okay, so last week we were able to derive the HJB, which I showed earlier, the stochastic HJB for this problem. And we can do that again. So let's do it for this case. So let's remember that the HJB is going to be taking the minimum over our control policy view of our infinitesimal generator. Maybe I was doing cursive A, V, which is our cost to go function, plus C, which is our control cost or our state dependent costs, and having this equal to 0. So in our case, we're using the exact same dynamics that we had last week. So the form of our infinitesimal generator is going to be exactly the same as the diffusion process that we looked at last week. And the only thing that changes is the form of our C, because we've included this state dependent cost. So writing this out, we're going to have partial t v plus taking min over u, and then our infinitesimal generator for our diffusion process is going to be u partial x v plus, and remember it's sigma squared over 2, coming from the second order Taylor series, partial x v plus, and now we're going to have our control cost, so plus cu u squared, and then now we're going to add our state dependent cost v, and this has to equal 0, and of course we also have to include our terminal condition, which is going to be this terminal cost here. I'm going to write it a little bit more generally because the method that we're going to discuss in today's session is something called the Cole-Hopf transform, and really the only particular cost that we need, a cost of a particular form, is having this quadratic control. But the form of our terminal cost is actually rather arbitrary. So I'm going to write an arbitrary CT x, and that's going to be our Vx capital T. So we'll specialize this to the case where we have quadratic terminal costs, but when we look at the Cole-Hopf transform, we'll just look at it in this more general case so we see the full generality. Or we approximate the full generality of this transform. So last week I was able to say I was able to propose a solution to our particular problem where we had quadratic control and we didn't have this phi term. We found a v that was we had a component that was quadratic in the state x. And also had this time dependent part added to it. That was the logarithm of the of time. That's a rather specific solution, but what I'd like to show you this week is for this case where we have a quadratic control cost, I want to show you a method called the Cole-Hopf transform that in most cases we can use to turn this nonlinear PDE into a linear PDE, which is really nice. So first off, let's arrive at that nonlinear PDE. Let's notice that our trick last week where we were able to find minimizing u by finding the vertex of a quadratic function still works because all of our terms in u, we have the highest degree is second degree, and then we have our first degree term over here. And so again, we can make the substitution u star is equal to negative partial xv to cu. So we can make that substitution. And remember, these terms here are going to combine so that we get partial xv squared over 4cu. We'll have our diffusion term, sigma squared to partial x xv. And now we have our phi term as well, which is that state dependent cost. So this is our nonlinear Hamilton-Jacobi-Bellman equation. And you see the nonlinearity comes in with this quadratic term here. But I'm saying that we can make a chain, we can express v in terms of another function that's going to give us a linear PDE for that new function. So this transform is something called the Cole-Hopf transform. It has applications in cases where you have a nonlinear PDE that has this quadratic term. So you also see it in and when you also have this diffusion term as well. So you see it in, for instance, like the viscous Burgers equation, which is a one-dimensional kind of analog to what you would see in fluid mechanics. And it also has an application here of the stochastic Hamilton Jacobi-Bellman equation. So what is this transform? We're going to make the substitution that Vx t is equal to exponential of some negative lambda inverse. So this is a constant that we're going to determine. We're going to tune it in a way that it cancels out the nonlinear terms of our PDE. So it's yet to be determined, but we'll derive it in a second. And then this is going to be some new function psi xt. So I've kind of defined our new function implicitly, but actually I just want to make sure that I might have this backwards. Yeah, I do have it backwards. Okay. Sorry about that.
So essentially the Schrodinger equation and then Schrodinger equation applied in exponential.
Yeah. Okay. Sorry about that. So I want to switch these two. So yes, I've defined our new psi explicitly in terms of v. And then if I wanted to invert this, define v, I would just have that this is equal to negative lambda natural log of psi xt. All right. So this is the Cole-Hopf transform. Okay, so let's see what this does for us. Going to plug this expression in for V in our Hamilton-Jacobi-Bellman equation. So we're gonna have partial T, negative lambda log psi minus partial x negative lambda log psi, this whole thing squared over 4cu plus sigma squared over 2 partial x negative lambda log psi plus b equals 0. And we can evaluate each one of these derivatives. So in this case, we can move our lambda just the outside. It is a constant after all. We're gonna have partial t of psi over psi. Right, this is the chain rule, and the derivative that we have for the natural logarithm. For this next term, something that looks very similar, we're gonna have negative lambda partial x of psi over psi for that whole thing squared over 4cu. And then in this next term, we're gonna have to take two derivatives of our natural logarithm. So let's do those one at a time. We've already found one derivative. And the first derivative is this. We can take that second derivative. We have that just this term here. We're gonna have negative lambda on the outside. So here we're gonna have we're gonna get psi squared, and we're gonna get a negative on the outside, and then we're gonna get another partial with respect to x on top. So the whole thing is gonna be psi squared, partial x, psi squared. So let's just write it as partial x psi squared. Right, and I think yeah. So when we have that negative, the negative cancels out here. And then our other the other part of this product rule is going to be, or yeah, the other part of the product rule is going to be negative partial xx psi over psi. So hopefully good with that. And our phi here. So now we have two separate terms. One of them is quadratic in lambda, and one of them is has just has linear as, or has lambda as a multiple. But we have two terms that are nonlinear, that are quadratic. We have this term over here, and this term over here. And what we want to do is we want to choose lambda so that these terms cancel out, right? So just to write it out, I can write 1 over psi squared on the outside. We have lambda over 4cu. Actually, let's just write partial x psi. That's that too. And then over here, we're gonna have sigma squared over 2 times negative lambda. Oh, you're right. Yes, thank you.
With a minus sign.
With a minus sign. Yes.
And there shouldn't be minus in the line above.
So it's negative lambda, so it's oh, you're right. Yeah, this should be. Let me just make it. I know that you're right, that there shouldn't be a minus sign, but I just want to make sure I just want to see where I made the mistake. Okay, so I think where I made the mistake is this was originally negative lambda. And then when I took that first derivative, I should have gotten two negative signs.
No, that's correct.
Yeah.
It's just the next line doesn't have the next sign.
This shouldn't have.
Yeah.
Hmm. Okay, I'm not quite,
You even explained it
I did,
when you were directing.
okay, okay. Yeah. Yeah, I agree that this should be negative, and yeah, this should be positive, okay, alright, I'm sorry about that. So we're gonna have negative here, plus, lambda, just plus lambda times sigma squared over two. And this should equal zero, that is the game that we're trying to play, we're trying to find a lambda for which this equals zero. So we can see that what we need is for lambda over 4cu to equal sigma squared over 2, which tells us that the right lambda to get this cancellation is going to be 2cu sigma squared. All right, so if we choose that lambda, this is the lambda that we're using, then we can write our equation for psi as, and I'm going to multiply everything by psi. And also multiply by lambda inverse. So what I get is partial t psi, negative partial t psi, minus, and so we've canceled these terms here. These two terms. And what we're left with is, yeah, minus, it's gonna be, so we cancel out our lambda and our psi, we have partial, rather, sigma squared 2, right, over here. Partial xx psi. And multiplying, our phi by psi and inverse lambda, we have, inverse lambda, phi times psi is equal to 0. So this is a linear equation. By the Cole-Opp transform, we're able to find an equivalent linear PDE that once we find this psi, we can apply our inverse transform up here, this thing right here, in order to recover our v, which is our cost to go function. So now, if we have a general terminal condition like psi x t is equal to ct x and some general phi, we can use all the methods that are available to us for linear equations in order to solve this PDE, such as Green's functions, for instance, or separation of variables, or whatever is appropriate for this PDE.
Interesting that we can shorten the equation of the result.
Yeah, yeah. Well, it is, yeah, it's the Hamilton Jacobi-Bellman, so there's probably some equivalence there, some connection.
So I have a quick question. So,
Yeah.
yeah, so it seems like there's magic lambda value through which we can write things down in a linear.
Yeah. Yeah, yeah, so it works in the case where we have a quadratic cost,
Yeah,
and also it's not always possible to find, in the 1D case, it's always possible to find such a lambda. But in the higher dimensional case, where you have a higher dimensional state space, it requires a matrix inverse.
yeah,
So that this lambda can't always be defined. But in the 1D case, you can always find this lambda. So if you want to look at the more general case, there's that Kaplan paper,
yeah,
where they do use the Cole-Opp transform, and they do it in a more general case, and then they tell you what what has to be true about your initial equation, whether you be able to find lambda.
Yeah, so maybe you explained already, but like, what was the, can you scroll a little above and? Yeah, and right here. Yeah, I'm just trying to look at. From what motivation we arrived, like, from which point we. Like, yeah, okay, well, what's the equation that we wrote at the top that led to lambda equals to that value? Again,
Okay, so. So the original thing is that we said that we're gonna. Express v in terms of a new function, psi,
yeah,
this equation right here.
Right.
And then we're gonna try to fine tune that lambda so that we get the cancellation of these two quadratic terms. This is an old trick, I think, the name Hoff is attached to it, so it probably goes back to nineteen thirties or 1920s or. And I think it might have originally had application in quantum mechanics.
So
right?
it's kind of convenient to go backwards. There is this formula for psi with exponential and try computing its second derivative.
Mhm.
So it's clear that when you hit it once with derivative, you'll have derivative of v appearing in front of the exponential.
Yeah.
When you hit it twice with derivative, you'll get second derivative of v, but you also get another derivative appearing, so you have v squared. And as a result, you can see one coefficient has kind of 1 over lambda, and the other has 1 over lambda squared.
Yeah.
And then you just match these two coefficients with whatever was.
Mhm.
Yeah. Right, and that's why it will not work in 2 dimensions, for example, in 2 dimensions. If you write such formula and try to take partial derivatives, you'll see that from this lambda, you get very strict relation between many coefficients. One lambda cannot count. Unless you're really lucky.
Yeah.
Seems very cool. Yeah.
Okay, nice, I'm glad. Okay, cool. So yeah, so we've found a new PDE to solve that is linear and that is fantastic. So let's see, the next thing that I want to.
Oh, but except this is not, this is like log of, no, exponential.
Oh, you're right, of course. Good catch. All right, so yes, so actually what we need to do is, rather we need to take the exponential minus, and so yeah, we can use, I'm just gonna write in terms of lambda, but our lambda is this. And then we're gonna have, it's our terminal condition. So for the time being, I'll just write this as, CTX. Right, so we also have to transform our terminal condition as well, in the same way that we transformed our V and our PDE, we have to transform it for our terminal condition. So I want to kind of talk about what sort of equation this linear equation is. So I've written this as negative partial t of psi, and that's to kind of get us to think about this thing running in backwards of time. Because if we think about this running backwards in time, and if I re-express it like this, move these terms to the right hand side of the equation, partial x psi minus lambda inverse b psi, then if this is running backwards in time, this really looks like a diffusion equation. So normally a diffusion equation that runs forward in time would look something like this. Partial xx u, and then maybe some diffusion coefficient alpha. But if we think about this as running backwards in time, which is what we're doing because we're integrating it backwards in time, we have a terminal condition. We're trying to find it for earlier t. Then this will look like a diffusion equation, just running backwards in time. So maybe we have some, maybe at time t equals capital T, we have some sharp spike like this, and then under the diffusion, this thing is going to smooth out. Maybe I should make the arrow going in the opposite direction. Yeah, it will smooth out over time. So this is t going backwards. And then the other term that we have here is this term that's proportional in psi. And so if we just kind of ignore this diffusion term, what we see is that these two terms are actually governed by an ordinary differential equation. And what this should remind you of is we know that something of this form can have a solution that looks like a exponential, and it's actually going to look like an exponential if phi is greater than 0. So it's a cost that we accrue from being in that particular state. And lambda, I should mention, is also going to be greater than or equal to 0. Because sigma squared is obviously positive, and CU is going to be positive as well. Then when this runs backwards in time, if we're in a state that has a non-zero value of phi, we're going to see that this decays over time, kind of exponentially. So maybe this is time t2, and then we go to some earlier time t1, and we get a decay over time. That's sort of what this ODE term is telling us. So there's kind of a decay term and a diffusion term, and that's what we have in this PDE is kind of like a decay diffusion term equation running backwards in time. So another way of kind of thinking about this is maybe we're thinking in terms of we can also think of this decay as like absorption, like where the value of the function c is being absorbed at these states, at these, wherever this thing is not 0. So some domain d which is s t, for which dx t is greater than 0. On these regions, we're going to get some absorption. And I want us to think about the case where phi is actually infinite on for some value of x and t, right? So let's think about this d infinity where this is actually infinite. It's the role of mathematicians to think very carefully about infinity, but I'm not going to do that today. I'm going to treat this kind of heuristically, and just to say that as this phi approaches infinity, we would expect this decay that we have to be instantaneous, to instantly have our psi drop from whatever its value is to 0. That's kind of the limiting behavior of this decay, is that it will drop straight down to 0.
Don't you size which have some derivatives for the equation to make sense?
Well, I have this here, or what do you mean?
Well, your psi, you're taking first derivative in t and two derivatives in x, so it used to be expected to be differentiable twice in x. And at least once in t.
Yeah,
So this continuity is a little bothersome.
yeah, it is a little bothersome. It is a little bothersome. I'm afraid that that's as far as I'm gonna go. Yeah, today. But that's all to say that the way that we can kind of treat these regions. Remember, we're thinking of this drunken spider problem. Done. Okay. Oh, we're doing good on time. The idea of this drunken spider problem is that we have maybe some pits or a lake or whatever where we have some feed that is infinite on these regions.
It's not enough to say that psi is 0 in those regions.
Yes, it is. It is. That's exactly how we're going to treat it. Is
It doesn't make problems.
Yeah, you're right. It does. It smoothly transitions. Yeah. Well, it smoothly transitions in this direction. I don't know. I don't think it smoothly transitions in this direction. I think it
Experiences t. And is that
this direction is x.
so in x is even smooth, it has two derivatives.
In x it's smooth. In t,
T has one derivative, and x has two derivatives.
but I don't know if it has a derivative at this point. Because the way, at least the way I treat it, when I was solving this, is I could have some non-zero value of psi. So psi greater than 0, right up to this point, and then I just set psi equal to 0 at that point. Because it's kind of causal, it's kind of a causal argument, like seeing the phi spike to infinity at a point can't like retroactively affect the psi before it. I know that's kind of a heuristic argument, but yeah, so it actually is, the way I was treating it, it's discontinuous in time at such a boundary like this. But Sergey predicted what I was going to say next, which is we can treat these domains where our phi goes to infinity, we can treat the boundaries of them as being boundaries of our domain to which we apply a Dirichlet, homogeneous Dirichlet condition. So what that means is our psi x t, psi x t is forced to equal 0 for xt in this partial d infinity. And then we've kind of restricted the domain of our PDE to be whatever our original domain is. So maybe r cross 0t, we're set minusing out our t infinity. Right. So we can look at this problem instead. And that heuristically, that kind of matches the case where we have phi is equal to infinity. So this is where these Dirichlet conditions, in kind of when we think of like a stochastic process, this is the case where once our like our Brownian trajectory crosses this wall, it's lost, it's absorbed, it's not re-entering the system. And so that kind of matches, so those are just a few ways maybe thinking about what the effect of this infinite phi is for our problem. Okay, maybe there's more to say about that, but I would like to just do one more thing, which is let's return to the case where phi is uniformly equal to 0. So this is the case that we were looking at last week. So phi is going to equal 0 for all xt, right, in our domain. And I just want to use this method of the Kohl-Hopf transform that we just derived, or that we just used to transform our PDE to try to reproduce the results that we got last week, just so we can do a sanity check that this does work. So our Kohl-Hopf PDE is we can write it as partial d psi minus sigma squared 2 partial x psi plus 1. Okay, and we don't need this term because we're setting phi equal to 0 everywhere. So we just have this nice diffusion equation to solve. And we're looking at a case where we're solving one of the reals, and some finite interval 0 to t. So what we can do is I can write down a solution in terms of a Green's function. So the Green's function is given by this PDE and the particular boundary conditions that it has. In this case, we're solving over the entire real line. So we just want, kind of decaying boundary conditions as we go out to infinity. So we can write out a solution, in the following form. Maybe Green's functions are new to some of you, but they're a very cool way of kind of formally inverting a differential equation and finding a corresponding integral equation. So we have our psi t x prime, and we're doing this integral transform with respect to the kernel g, which is our Green's function. In order to propagate our terminal data psi forwards or backwards and so on. So over the reals. And this is going to be equal to our psi t s. So for some t that is less than root 15. So the Green's function for the diffusion equation over the entire real line looks like this. It is a normalized Gaussian function. So it has a integral 1 over the real line. And it is going to be sigma squared over 2 times pi t minus t to -1/2 exponential of -1/2 sigma squared t minus t x prime minus x squared. So in particular, if we're integrating over x, this integral transform is actually a convolution, because the dependence of g on x prime and x is just dependent on the difference between x, the absolute difference of x prime minus x. And rather than trying to, and also again, or another thing, we're looking at the case where psi t x prime is equal to the quadratic, like we were last week. So quadratic in the terminal state. Sorry, not psi tx. That's our our VTX. Our VTX is quadratic in the terminal state. So our psi is right. It's going to be exponential. And let's write out what inverse lambda is, which is 2cu sigma squared. So 1/2. Write it like -1/2 x squared cu sigma squared times ct. Yes, times ct. Right. Yes. From this right here. Times ct. So rather than trying to rather than working through this whole integral, this whole convolution, let's just make use of a fact, which is this is almost a normalized Gaussian function. It's just missing this coefficient that we have out in front. This g is it is a Gaussian function, and this is just missing that coefficient. And we have this nice fact that's very familiar to probabilists, which is if we add two normally distributed random variables. So if we add some x independent normal variables. So we have some x that's mu1, x1 is mu1, and it has variance sigma 1 squared. And we have x2, it is normally distributed, and it has mean mu2 and variance sigma 2 squared. Then the sum x1 plus x2 of these independent random variables is normally distributed with mean mu1 plus mu2 sigma 1 squared, variance sigma 1 squared plus sigma 2 squared. And why that's useful here is because this act of taking a convolution of these, we can interpret them as probability density functions of the normal random variable is equivalent to adding two independent random variables. So that kind of says that we can just examine the mean in either case and examine the variance in either case and just add the means, add the variances, and find out figure out what the results is going to be. So what we're going to have is that our psi t x so actually let's figure out what that mean. Well, so in either case our mean is going to be 0. This is not our mean, this is the kind of dummy variable that we're using for our convolution. So in either case our mean is going to be 0, and so then we have that our output mean is also going to be 0. And we can also add our variances to figure out what our output variance is going to be. So here we have variance of Cu sigma squared, so over here, Cu sigma squared over Ct, to which we add this variance over here, which is going to be sigma squared t minus t. This is our let's call it sigma 3 squared. Right, that is our that's going to be the variance of our results of our resulting Gaussian function. So we can write that out, -1/2, and then I'm just going to plug that variance in down here. So Cu Ct inverse sigma squared. Actually, let's just write that out. Sigma squared out here, because we can factor it out. T minus t. And then we'll have our x squared up top. And then we also have to write out our 2 pi, the square root of 2 pi times our variance. So Cu Ct inverse sigma squared. Let's write that. Well, I'm making a mess now, but yes. Okay. Sigma squared out there. So just Cu Ct inverse, and then t, big T minus little t. And then we were off by that factor. This was not truly a normalized Gaussian to begin with. So what we're going to have to do is we're going to have to put in our numerator just square root of 2 pi times the variance of this thing. So in this case, just Cu Ct inverse sigma squared. Okay, and now we can look at we can actually produce our v tx by doing that inverse operation. So so we're going to have negative 2 c CU, I believe. Lambda is equal to -2 CU. Sigma squared. Times natural log. We have cancellation of the 2 pi, and yeah, cancellation of 2 pi and the sigma squared here, so we can write square root of CU CT. Actually, what we also do is we can multiply it through by CT and the numerator and denominator, so we have CU. We have CU, we have plus CT, T minus little t. Times exponential of let's write it out as -1/2 sigma squared CT x squared over CU plus CT times T minus C. Now we can use properties of the logarithm to turn this product into the sum of logarithms. So let's start by writing this expression over here. So this is going to be a sum. This product is going to turn into a sum. We're going to have a logarithm and followed by an exponential. So because the logarithm is the inverse function of the exponential, those things are going to cancel each other out. And that is going to leave us with a negative times a negative, sigma squared over sigma squared, and then this remaining CU. So we'll have, hopefully you follow me when I write CU CT over CU plus CT times T minus T x squared. Okay, so there's our quadratic term, which we had before. And so we're left with a logarithm out here. The way we're going to treat that is we have this property that we can take this factor out in front, and that's going to be an exponential of the argument, or a power of the argument of the logarithm. So that leaves us with CU sigma squared. Natural log, the power of 2 is going to cancel out the square root. The negative is going to invert this argument. And we're left with CU plus CT over T minus little t over CU. So that is what we claim our VTX is, and let's just see. Okay, memorize what we have there. Let's just see if that actually matches what we got last session. And so we have this CU plus CT over T minus, or times CT times big T minus little t, quadratic and x, plus this natural logarithm term, and I do believe that is what we were able to derive. So there is proof that the Kohl-Hopf works in this special case that we were looking at last session. Okay, so all that I have left for this week, and it is, already 5, we did get a little bit of a late start, but I have some numerical results for the solution of this case where we have a phi that is infinite on some domain, right? So we have some phi, yeah, basically xt is equal to infinite, and this is not the empty set.
And we're looking zero side.
Phi. So phi is our state dependent cost function. So this thing, so it's in, so what I have, oh, sorry, what am I plotting?
On this color plot.
Yeah, okay, let me explain. Yeah. Neither, actually. So just to explain first, there are some non-numbers that are appearing in this as a result of this simulation. What I defined was this rectangle here to be the region where phi is equal to infinity, and also here, right? So on these regions, phi is equal to infinity.
So there's no numbers appear because the problem for the differential equation was imposed. Because you have second derivative, you need to specify this boundary not only value of psi, but also its first derivative.
So I would say the reason why numbers are not appearing here is because in the process of solving this equation, psi has become 0. And so when I take the natural logarithm of it, it's going to return infinity.
Well, that's what it has to do, you're plotting psi or v.
I am plotting the, I'm plotting the control uxt. So as a reminder, uxt is equal to negative partial x of v over 2c
Oh,
u.
you'll go crazy, I don't know. Yeah.
Yeah, so that's what I'm plotting, is I'm plotting the control that you're gonna take at point xt. Right, so this is the feedback control. It does produce a really interesting looking plot. So what you would have up to this period right here, we're kind of looking at this backwards in time. Up to this point, it's going to correspond exactly with what you would have for just the case where phi is equal to 0, because this thing is only really seen downstream or upstream or however you want to look at it. But once we get to this point over here, so when it's blue, that corresponds to a negative control, and that's telling us that it is trying to drive the state in this direction, trying to drive it downwards. When it is yellow or green, one of these warm colors, it is trying to drive it up. And it's a little bit clearer to see over here that once you approach this gap, there is a line where if you are north of that line, it's time to go in through that gap. And when you are south of that line, it's saying let's commit to going below that gap.
And if you're close to this line, you just give up, because there's no way out.
Yeah, if you're close to the line, yeah, it's like it's like this
So that's this white region outside of your domain, that's where there's no hope.
You mean like out here? Like out here? Or,
No, you had the rectangle where phi was infinite.
oh, you mean out here?
Right?
Yeah.
Well, in both of these, there's a clear rectangle.
Yeah.
And then there is, but white area is larger than the rectangle. So the
Yeah,
white area,
but-
which is outside of the rectangle, is the region of no.
that is more due to a numerical error, I would say.
Well, there isn't this numerical error.
Yeah.
Just as the fact that this white region at the bottom sticks slightly to the left. You
Yeah.
see, there's three regions there secretly, one above where you can escape up, one below where you can escape down, and one of no hope.
Oh, I should say that this is actually extending all the way out to positive infinity.
Yes. So the region with no hope clearly gets larger,
Yeah,
it's
yeah,
this
yeah.
wedge.
Yeah. Yeah.
Well, actually, you can have you approach infinite, right, along the vertical line going out.
You would become approach negative infinity.
These lines probably due to like the value is too large to.
Yeah, like numerical.
Yeah, it's
Right.
I think it's a numerical issue. It's producing infinity for that value, because I am taking the logarithm of something that's approaching 0, and so that's going to get close to infinity. And actually, so when I was doing these, when I was simulating these diffusion processes, right? These you see this trajectory here. It doesn't always work. So what we should have is in the case where we have and this is due to a numerical error. And I need to explain this a little bit further. So I'm solving this heat equation in just kind of the naive way that you solve the heat equation explicitly, right? So I'm using a finite differencing approach. I'm approximating the second derivative, by doing 1 times the value to the left minus 2 the current value, or maybe I got the sign wrong there, plus 1 to the value to the right. Just the naive kind of finite differencing approach.
If you optimize the difference in time, step in time and step in space.
I'm only making sure that I am not getting numerical instability. So there's a condition on that, right?
Yes. Besides instability, depending where you put it, there's also optimization in the side of step.
I didn't do any optimization. I just made sure that I was satisfying the constraint for stability. And actually, I can show you that my results are pretty good. Because up to this point here, where this corresponds to a different problem where I set the boundary kind of back here. Up until the point where I actually see the boundary, it corresponds perfectly with the case where I have no barriers. Where I had an analytic solution to the problem, and then this cost to go with the barriers is found using the finite difference heat equation. And, really good correspondence there. But that's how I'm solving the heat equation in this case. I tried finding analytic solutions, but I gave up after a while. But let's see, what else to say about this? So actually, when simulating these trajectories, they're maybe about like half the time, these actually would crash into the boundary. And then it would plot what I have up to that point, but then, but yeah, it failed. In the ideal case, it would not fail. Because as I get close to these boundaries, because of that Dirichlet condition, that really forces the solution to go to zero. I don't know if it would fail like out here, but at least in here, it would not fail. Because it's gonna force the psi to go to zero, that Dirichlet condition, it's gonna force the psi to go to zero at this point. And that's gonna, when I take the negative logarithm of that, that is gonna create a log, what people call like a log barrier, which is a way of simulating a hard constraint, a hard inequality constraint for an optimization problem. This zero is gonna go to positive infinity, which means that my control is gonna become infinite. There's no way I should be able to escape. There should be a zero probability that I'm actually able to escape into the no-go region. But I'm not solving this stochastic equation with an infinitesimal time step, but rather a finite time step. So there is a possibility that it can escape into those no-go regions. But yeah, I think these are really beautiful plots, and I have the code available here. So I can change my value sigma. What I did find is if I make sigma too small, it doesn't work. And I think that's because these regions here, so if I run this, sorry.
That's Python?
It's Julia.
It's Julia, you don't use sensitive notation.
Yeah.
Yeah, it's actually discouraged from the software engineering point of view.
Yeah. But we see it actually fails in this case, and I think it might have something to do with this boundary region shrinking too much and not being captured by the finite differencing scheme. I'm not exactly sure. It could also be that I haven't specified the control correctly, but I was checking out this morning and it really seems like I was specifying the control correctly. But yeah, if sigma's too small, then it doesn't avoid the gap. But if sigma's too large, then because what I'm doing is I'm solving the heat equation and I'm interpolating those values from the heat equation to produce a control function. So if sigma's too large, it could wander outside of the domain where I haven't solved the heat equation because I'm solving it on a finite domain. So yeah, so there's a nice Goldilocks zone where you can actually specify sigma and it should work. So here's a case where it fails. If I run it again,
But how's that's not a contradiction, right? You said that statistically you will not fail.
It really should.
Your psi is kind of averaging all these trajectories. You design the control for this averaging, kind of the best you can for your expectations. But you do fail, and you fail often.
So my intuition is that it shouldn't, like the event that it fails should be like probability 0. Because of that log, because the effect of a psi going to 0 is to produce a control that goes to infinity, right? U is going to go to infinity. Also, its first derivative, because the derivative of logarithm is also to be infinite. And that control should be infinite in the direction that you need to, right? So it's like this case here.
then your equation doesn't apply.
What's that?
Then your equation doesn't apply. The equation requires two derivatives. Okay. And you are saying that your derivative on one side is zero, on that side is non-zero.
But inside this domain where I actually have, where I'm realizing my trajectory, the derivative should be well defined because I'm taking the derivative of the logarithm of a smooth function. Or at least a logarithm of a function that has its second derivative. I mean, it's a numerical approximation. But I think just in the exact case where you have exact solution to the equation, yeah, what you have.
It just fails due to discrete time.
That's what I think.
That's
Because
the way out.
Yeah,
So
but-
we don't understand something.
But-
But I think the fact that we're talking about like expected cost, if it has a non-zero probability of falling into that region, then the expectation is not defined, right? So I think the fact that it works.
Right,
out,
yeah.
It
The expectation
will not-
would be infinite,
yeah, I
it would just overwhelm.
the probability of falling into that infinity regime is zero, should be zero.
It should be
Otherwise,
measured zero.
otherwise, the expectation will not be defined.
Right, because that cost to go function, because you have some non-zero probability of getting an infinite cost, it should just make that whole cost to go function infinite.
Exactly, which means that your algorithm should not produce such trajectories
No, it shouldn't.
ever.
No, it shouldn't, yeah, so that's due to, I think, just the numerical nature of my solution.
No, no.
Well, I'm sure I could do better, but I had a finite time.
such a thing. It is,
Trust me, I haven't accepted it. I just had to produce something for today. But I hope this is interesting. I can release my faulty code to for you all to experiment with.
I think you'll derive a lot of satisfaction in analyzing how well posed your differential equation problem is.
Okay.
And how it compares to this wage boundary.
I think. I agree.
And eventually you'll be able to produce as a result a code which you can use for airplanes. They will not fly into that region.
Yeah, so I mean, yeah, I guess that's a good takeaway from this, is that you have to be careful about how you implement these
I-
analytical results.
That's a very specific question. So technically, like I'm seeing, like right in between, it looks like white, but it shouldn't be white, right? Like if you're right at the boundary, you should either choose to go one way or the other,
You should.
not stay there,
You
right?
should, but the nice thing here is that the chance of you staying right on the boundary is like an event of measure zero, because there's a random perturbation here.
Yeah.
You're right, like,
Yeah.
you would really, like, if there wasn't any noise, you would be stuck. You'd be stuck
Yeah.
unable to decide if you go to the left or right. But we do have this random perturbation that will force us to go one way or the other.
Sigma is the perturbation, right?
Sigma is the strength of the Brownian motion, yeah, the Brownian motion component of the diffusion process. Yeah, so sigma is one in this case, I can tweak sigma, CT is the gives us the terminal cost. That coefficient for the terminal cost. But yeah, I included my code from last week in the box, and I can include this as well, so.